Hello and welcome. We're going to be getting started with our webinar shortly. Before we get started, I'd love to tell you all about some upcoming additional webinars we have. Next Wednesday, March 17th, we've partnered with Michigan Center for Occupational Health and Safety Engineering and Dr. Nadine Sarter to offer a free webinar on human-machine teaming, how and why it breaks down. Also on Wednesday, April 7th, we've partnered with the UC Berkeley's Labor Occupational Health Program's School Action for Safety and Health, or SASH program, for a webinar on exploring COVID-19 vaccinations. And on Tuesday, April 13th, we'll have our next Industrial Hygiene ERC webinar. We've partnered with New York, New Jersey Education and Research Center and Dr. Brian Pavilonis to offer a free webinar on estimating indoor transmission risks of SARS-CoV-2. For more information about these upcoming events, you can visit us at coeh@berkeley.edu/about-CE. And on behalf of the Education and Research Centers throughout the country, we're pleased to present the Industrial Hygiene webinar series, offering free webinars the second Tuesday of each month. This collaborative effort is on behalf of each ERC's continuing education program and aspires to provide access to current research supported through NIOSH ERC programs. Thank you so much for being here today. Today's webinar, Respirator Development in the Time of COVID-19, is brought to you by Heartland Center for Occupational Health and Safety, the University of Iowa. A few housekeeping items first. You will be muted during this presentation. If you'd like to ask a question, please enter it into the online Q&A box. And we'll be saving time at the end of the presentation to address as many questions as possible. This presentation is being recorded and will be made available on the Center for Occupational and Environmental Health YouTube page, and slides will also be available. All participants who logged in with a registration email for the full live presentation today will get an email tomorrow with the link to the recording and an evaluation form that will qualify you for a certificate of completion with 1 continuing education contact hour. Once your evaluation is completed, you'll be able to access and print your certificate. And without further ado, it's my pleasure to welcome our presenter today. Professor O'Shaughnessy joined the faculty at University of Iowa in 1997, where he's a faculty member in the Department of Occupational and Environmental Health. He obtained licensure as a Certified Industrial Hygienist, or CIH, in 2008. With over 75 publications in peer-reviewed literature, he's a recognized scholar in the field of aerosol physics and human exposure assessment applied to occupational and environmental health concerns. One aspect of his current research is associated with evaluating the effectiveness of filtering facepiece respirators in various work environments, and most recently, their effectiveness for protecting the wearer from inhaling the COVID-19 virus. Thank you so much for joining us today. We're looking forward to your presentation.
Okay. Well, hello, everyone. It's certainly my pleasure to give this webinar on a topic that I think, and you all probably agree, has had considerable importance over the past year, and certainly will continue to be relevant into the future. I have to say that here in the Department of Occupational and Environmental Health, we try to give our graduate students some opportunities to give oral presentations on their research, and try to do it in a way that's meaningful to a general audience, to kind of translate the science, as they say. So I typically say to them, explain it like you're talking to your mother. Well, for this one webinar, my mother is listening in, so I hope, anyway, I passed my own test. And hi, Mom, and let me know how I do at the end. Thanks. Let's see, I'm going to share my screen now, and we'll get started. So brief outline, I thought I'd bring everybody up to speed. What is an N95? Let's start from the basics there and go with that in terms of the fundamentals of that particular type of respirator, and then jump into the consequences of the COVID-19 pandemic as it has affected the N95. Talk about testing the N95 and some alternatives, and then I'll wrap up with some ideas about current and future concepts that are going on right now. So the fundamentals, according to the National Institute for Occupational Safety and Health, NIOSH, they're the government agency that approves these devices, so that they all have a certain quality. They pass certain acceptance criteria. They call these things filtering facepiece respirators, FFRs to be specific, and they quote, the N95 respirator is the most common of the 7 types of particulate filtering facepiece respirators. This product filters at least 95% of airborne particles but is not resistant to oil. So first of all, notice the blue N there. As far as I know, that's where the N in N95 comes from. It's not resistant to oil, so you can't use this in a machining plant with a lot of coolant fluids floating around, that sort of thing. But what about the rest of this sentence? This product filters at least 95% of airborne particles. So kind of exactly what does that mean is what we'll explore here initially. So does, obviously means something about removing at least 95% of things. It's got to be at least that efficient at capturing particles, which means 5% of them can get through, right? But is that on a count basis? Do you just count up all these particles, or is it by mass, the total milligrams of them that get through? Is it for all particle sizes or some sizes? So let's kind of dive into that a little bit. So getting into what's called the aerosol physics. Yes, it is a branch of physics. Got a lot going on there in terms of just these little tiny particles that can float around in the air. They've got mass, they've got inertia. They're interacting with molecules in the atmosphere. They can get bounced around by them. They scatter light. But they can also obviously be captured as they're flowing through a airstream towards some inanimate object, right? That's in their way. And so obviously that's what's going on here in terms of a filter, but you can see that there's at least these 5 different forces that can be applied to capturing particles with a filter. And very basically, very briefly, you can think of obviously that they consist of strands, fibers, and that again, the particles are moving towards them in an airstream. You're sucking literally through this N95 that's on your face. So the air has to go through the fibers, and the particles are hopefully being entrained onto the fibers themselves. So diffusion, for example, is where the particle is so small that it is getting bounced around by air molecules, which are constantly moving themselves. So they're so small, they're getting interacted, literally pushed around. They kind of randomly find their way to the strand. It's actually a very strong force for the really small particles. And then on the flip side, for larger particles, they're acting like cannonballs. Once you put them into action, move them in a certain direction, despite the way the air is going to flow around the strand, the particles are going to, nope, they're not going to make the turn and just smack into it. So that's impaction. So then you build up, in terms of modeling these things mathematically, or even physically, obviously the filter itself is a mesh of these different fibers of a certain thickness. And so then you can move to trying to mimic or design filters of a certain thickness with certain strands of a certain size. And then, how porous are they? You've got to let some air through, right? They can't be just a rock wall. So all that, it comes into play in terms of designing these things, and they are not trivial. I think a lot of folks I've found over the past year kind of considered this to be a trivial problem, and that it was easy to overcome. And actually, there's decades of science has gone into the development of N95s to give you that balance between good efficiency and breathability. Those are the two kind of yin and yangs of filters. Now here's some scanning electron microscope photos of an N95. It's typically, if you have an old one, take some scissors to it, cut it open, you'll see that it's not just a single layer, typically the better ones. So the outer layer, it's a cup-like thing, so it has to kind of support that cup. And so the outer is a mesh. You see it's very fairly largish diameter fibers, very porous. It's there to again kind of hold the thing open. The middle layer is doing all the work. So you see this is all on the same scale. Now you can see extremely small strands. I don't know if you can see my arrow here, but the smallest ones are 1 to 2 micrometers. So that's a millionth of a meter. These things are extremely small, non-woven mesh, they call it. So we're having a kind of a tortuous path, as they call it, to trying to capture particles as they go through this layer. And that's electret means that they are charged as well. And we'll talk about that in a minute. And the inner layer is going to be kind of a nice, smooth surfaced polypropylene. These are all polypropylene strands. And again, it's mostly just to protect that middle layer, especially from your moisture from your breath and other things that are going on inside. So then just to give you a scaling here before we start talking further. So on the right is the human hair blown up. If you cut that thing widthwise, it's about 50 to 70 micrometers. That's about the smallest little black dot that you can see on white paper. So that's the start of this. Is you're in the visual range just barely. The very, very fine sand particles. And you're marching down the way here through different blood cells, bacteria, and then finally you get way down here, this little red dot is the virus that we're concerned about in its raw form, as that virion, they call it, that little circular thing with all those things popping out of it that you see so often. 0.1 to 0.2 microns, that is, so now we're down in what's called the nanometer range, a billionth of a micrometer, of a meter, excuse me. So this is 100 billionths, or 0.1 micrometers, extremely, extremely small. These are like macromolecules. So now, just talking about the efficiency relative to size, because that's part of the question you asked up front. And on the scaling down at the bottom here, you see particle diameter. This is a log scale, so the size is jumping up kind of exponentially. So 0.1 is down at that virion size. You can see diffusion, that's what we're talking about here, is extremely efficient for the very, very, very small particles. 100% are being captured. That's what it's showing up on the top left. So it's not true that N95s get less and less efficient for smaller and smaller particles, which would be intuitive, that the super small ones get through. That is not true. The super small ones actually start getting captured by this diffusion mechanism. Meanwhile, the inertial kinds of forces, impaction and interception gravitation, they take care of the big particles. You can see they get up to 100% efficient, around 1 micron or larger. So there's this huge dip in the middle where you could get a lot coming through. But along comes the saving force here, which is charging. So when you charge the fiber, it acts like a magnet kind of scenario where it pulls in and attracts these particles before they can get through. So now we're up to just this tiny little dip up here. And this is true of all filters. They all have a dip like this where there is the least efficiency. And they call that dip, or where it's at the most penetrating particle size, the MPPS. And for modern N95s, it's down around 0.03 to 0.05 microns, extremely small. So these are the only particles that are going to get through. Most of the others you see are captured with 100% efficiency. We're worried about the virus at 0.1 to 0.2. It's up there at 99, almost 100% efficient to capture, again, the smallest possible. A lot of them are in droplet form, as we've discovered, right? And so those droplets are even larger. They're way up there and easily captured by an N95. Just for comparison, if the media is not charged, you don't have this orange line. You're back to this situation here. It's like, well, what do we do now? What you have to do is take that diffusion, that red line, and push it to the right. That's the only option you have. And the only way to do that is to thicken the filter. Now, what happens when you thicken it? It gets harder to breathe through. So see, again, this is the genius of a modern N95 is to prevent, is to have that high efficiency without having something that's impossible to breathe through. So backing up now, this is what it would look like if it wasn't charged. And your MPPS shifts to about 0.3 microns. Now, many of you might go, aha, I've seen definitions of an N95 saying something about being 95% efficient at 0.3 microns. Well, as I've just shown you, that's no longer true. As a matter of fact, here's a study by Sami Ranganasamy. He is the NIOSH N95 guy. He knows everything. He's done a massive amount of work over the past 2 decades. He says, some studies have reported the most penetrating particle size of 300 nanometers for fibrous filters. However, recent studies have shown them down at 40 to 60, like I'm showing you. And so the 300 nanometers is not correct anymore. So it's an obsolete concept. Okay, so now how do they test these filters? Again, Sami and his group there, Dr. Ranganasamy at NIOSH know this very well. They helped develop the procedure, and they start with sodium chloride table salt. You make a solution of it, so now it's dissolved in there, and then you nebulize it into droplets. Now you've got these little liquid droplets, out there. You put it through a drying column or something to evaporate off the water, and you end up with little salt crystals. It's exactly what happens when oceans spray out and down there at the beach or something. So they test 20 filters. All of them have to pass. It's a pass-fail system. They have to all have the criteria of being this 95% efficient or greater. They tested 85 liters per minute. That is your inhalation flow rate when you're out jogging. Let's say it's not super exerted, but it's heavy breathing. So this is a kind of a worst case scenario that they developed for industrial situations. The size of the particle needs to be down around that 0.1 micron region, a little lower actually, 0.075 microns. It's, again, pushing it to the left of those diagrams I was talking about, but close to that dip. That's the whole idea. Get it, try to figure out where they're at their worst, not where they're at their best. And they do it with this device called a photometer, which I'll explain a little bit in a minute here. So you obviously need to measure the concentration of the atmosphere that you're pushing towards the filter. That's the upstream concentration. You measure it downstream, and the downstream should be 5% of the upstream. That gives you 95% efficiency. So that's a fairly easy calculation at the end of all this. So that's the test. Now, from all this, in what I've told you before, you would expect, and based on the original definition that I gave you, which is, they need to be 95% efficient or greater, at least 95% efficient. And so this is one way to think about it, that little dip there is the lowest it can go for any size. So now we know for sure that it varies by size, but that at its minimum, it's at 95. So these things actually are way more efficient than 95%. I hope that's what you're getting out of this, especially for anything larger than 1 micron, which is the large majority of particles out there in industrial situations. Even large bacteria are up here on the right, and so they are capturing just about everything, as long as there's no leaks. So it's not quite like this, though, in reality. What is happening is they throw a distribution of salt particles at the filter. So some are really super small, some are large, most of them are around 0.075. And so the idea then is that the total upstream concentration relative to the total downstream concentration gives you that 95% efficiency, or only 5% of them get through. So that's what's really going on. Now, getting back to what I just showed you about that dip, the dip may not quite correspond to the mode or the peak here of the aerosol size distribution. So just a little nuance here. You can take it for what it's worth. This dip can go a little lower than 95% because it's actually evaluating most of the particles where it's actually a little higher than 95%, if that makes sense. So again, take this for what it's worth, but it's very close. They obviously tried to get it as close as they could within the constraints of the aerosol generating device. Actually, I'm pretty sure is what's constraining this. Okay, so now with that as a background, let's get into the pandemic consequences. And I think we have to start with the shortage, of course, right? I mean, that's what this is all about. I wouldn't be talking to you if there wasn't a shortage. In an article I found written in September, this is what they decided were the main issues associated with the shortage itself. The government hasn't used the Defense Production Act on N95 masks. They didn't force the production of them. Here's a biggie. Hospitals cut costs by purchasing equipment on an as-needed basis rather than creating a stockpile of PPE. So it's a just-in-time, marketing situation or purchasing situation like any other industry, which cut costs, great, but prevented this stockpiling of PPE as a result. Apparently, the Health and Human Services funded the invention of a machine that can make 1.5 million N95s per day. But then the design, when it was completed, the government didn't purchase it. I've never heard of that one. That's what they're saying here. But this makes sense too. Without long-term guarantees that the government will keep buying respirators, the manufacturers were wary of investing too much to boost production. So they would have huge machinery sitting around doing nothing if there wasn't a continuous use of them to keep pumping them out. So they didn't have the production, up capable when we needed it. And then finally, the makers themselves, of course, they have a lot of proprietary information. As I said, they got decades worth of R&D into these things, and they weren't going to give that out just willy-nilly to anybody who wants to start making N95s. So that was a problem as well. I don't mean to knock the manufacturers at all here, though. This is just kind of the reality that popped up that created the shortage. I think we have to go back to number 2 and perhaps number 1 as the main culprits here, more so than anything to do with the manufacturers. So we didn't have it. Obviously, the stockpile really wasn't there as well developed as it should have, and we can get into the politics on this too, but that's another whole topic area, right? And this was not something that just, wow, hey, in 2020, this is something we need to start thinking about. No, this, as you see here, these are reports and papers going back to 2006, obvious need for stockpiling the N95s for any kind of influenza pandemic that we are kind of in now, right? So even also talking about reusability of face masks during an influenza pandemic. So there's what I consider to be one of the big crimes of the past year is, because it had ripple effects all the way down through the line. Okay, don't wear masks up front because we need to keep them for the healthcare workers. Okay, and then we don't have them enough for the healthcare workers, which means we certainly don't have enough for industrial uses where they've been typically using them anyway to do their job and keeping their protection there. And then it has something that affects on what was left to the general public, et cetera, et cetera. So this is huge as far as I'm concerned. So now we have to shift gears here towards the healthcare world, because this is obviously where the real concerns were amongst the healthcare workers, the people there that are obviously fighting the pandemic. And so they were issued and have been issued for years something called a surgical N95. So here you see from 2018, NIOSH and the FDA streamlined their approval process. So now we got the FDA involved is what this means. Okay, that both agencies have some sort of regulatory oversight on the N95. Actually, NIOSH in terms of approval, FDA in terms of regulatory issues. And the other big thing here is that unlike, I use N95s, carpentry and other things, just for whatever things I've been doing around the house and in my previous life as a carpenter. I never thought about single use before. I take it out and use it for 4 or 5 days. If it's still working, why not? Not so in a hospital. Okay, so the idea, obviously, you use it for any amount of time. You're ostensibly using it in an area where there are viruses floating around, so the thing is getting contaminated. So it was, and always has been thought of as a single use. You use it, throw it away. So this adds to the problem if you don't have enough already, and you have to chuck it out immediately after its use. So again, just getting into the surgical N95 a little bit more, it was designed off of the N95 as I've just described it, with additional criteria established by the FDA because of the considerations of the hazards within a hospital setting, of which you could be splattered by fluids of all different types as one thing. So it has to have pass a test for resistance to fluids. And they use synthetic blood for that testing. It also has to pass a certain bacterial filtration efficiency. So here's a graphic out of a 3M bulletin, and I'm going to use this to say, this is for educational purposes only. Please do not sue me for copyright infringement on these. I try to quote everyone below here in terms of the source. But so here you can see that there's a surgical mask, which I haven't talked about yet, but that's the thing that we've all, or some of us have been able to access. It's that square rectangular looking thing that allows some filtration but also the resistance to fluids. And then on the flip side is the N95, which they didn't care about fluids. Matter of fact, it's not even very good for oily things, as I talked about. And then there's the surgical N95 is kind of taking on both of those processes together. So it's a special N95, and it's usually got this blue color to it like this. Most of them, at least the ones pushed out there by 3M, which is the major manufacturer in the country, on top of only a couple others, Moldex, Honeywell, and North maybe. So very few of them actually in the country. Back to the requirements here on the surgical N95. This is from ASTM 52100 that dictates this. And you can see it does have a bacterial efficiency greater than 95%. So that's good. It's also somewhat like an N95. And it's even got a sub-micron particulate filtration efficiency down around 0.1, which is getting close to that 0.075. So this is the mask too. So this is incorporated within the N95 kind of requirements, kind of layered on top of it, and in terms of additional restrictions. And of course, you see their resistance to penetration by synthetic blood, et cetera. And these masks, you see, come in different levels. So I'll admit here in this table, I'm mixing up these two concepts of the N95 and the mask, but just to kind of give you a feel for how they are directed by the FDA. So along comes the pandemic, and people have to jump into action. And so now we have the FDA involved, right? So they have what are called EUAs, emergency use authorizations. So they have the power to quickly make decisions about things that need to be done in a situation like this where quick decisions need to be made. And you can see here that one of them had to do with decontamination for reuse. So this is back in June. They reissued this, they revised which types of respirators can be decontaminated. But on top of this were EUAs for different decontamination processes. So here's a solution, is what it comes down to. We don't have enough masks. They have to be used, they should be thrown away, but we can't do that. So how can we keep reusing them? Well, we have to decontaminate between each reuse. So here's, this is how they did it in many cases. Racks full of used N95s. They would go in there with, say, a vaporous hydrogen peroxide, vapor form, to just literally fumigate the entire room. It worked very well. They have the studies to show they killed off the virus to a certain percentage as well that they have to worry about. Log 3, log 4 reduction, that kind of thing. There's also an ionized hydrogen peroxide mister kind of thing. It's a little slightly different technology. Moist heat can also do the job, as well as UV light. So all of those were put into play to take care of this decontamination process. Here's a little fact sheet just recently put out by Michigan State University in their system. You have been given a decontaminated N95 respirator that has been decontaminated using a decontamination system that's authorized to decontaminate compatible N95 respirators. So again, this is what some of the push out to the healthcare workers who were forced to reuse them, and maybe a little skeptical about it or whatever. So now in this process, obviously they had to prove that the sterilization was effective, but what about the device itself? Does it cause structural failures? Do the straps still work, or do they get corroded? Can you actually reuse it? Does it cause it, help have a good fit? Does it keep that seal around your face? And does it still meet the NIOSH criteria? Is it still an N95 as I've described to you? So this is where I came in terms of the research that I was doing. Prior to that, past 10 years or so, working with a respirator, especially for use in agricultural settings here in Iowa. Agriculture is a big thing, so that was one of the places I was focusing on. So I had the equipment in my lab to test efficiency, and word got out fairly quickly of that being the case, and I was asked by multiple entities to help them with this issue, along with others. So now we get into the N95 testing process. Again, I've already kind of briefly described it to you, but if you had to do it right, if I had to do it right, I would have bought one of these. This is the TSI Instruments. This is the major manufacturer of the automated filter tester. This is what NIOSH uses. You can see how they have a plexiglass case here to hold an N95 that's sealed at the bottom, so there's no leakage around it. All the air goes straight through. They force that 85 liters per minute through it, along with the salt aerosol, and it's got the built-in photometers, one on the top, one on the bottom, to give you an efficiency automatically. The only downside to this is the $90,000 it takes to buy one, and they only make, I guess, I don't know, not many. They're definitely backlogged right now. I know that much. So this was not available to me, so I did kind of an in-house approach. But before that, just to say, what are these photometers? If you start at the top here, you put aerosol down through the yellow tube at the top. You can take advantage of the fact that particles do reflect light, or they refract light off of them. And they can use photodetectors to detect that refracted light. And by manipulations of mathematics and other things, literally tell you a certain mass amount, not the count, but just kind of incorporate this entire cloud as so much concentration of the aerosol per cubic meter of air. And so of course you do this above, you do it below, and you can get your efficiency. So this is the official method. My method, as it says here, uses what's called a scanning mobility particle sizer. So I'll talk a little bit more about this. It's sitting in the background there, along with two different ways of passing particles through the media. One was to use a little sample or a tester using just a portion of a mask or a portion of a filter material, basically squeezing it between two columns and measuring the atmosphere above the filter relative to below. This is after nebulizing in exactly the same way that the TSI instrument does to get your 0.075 micron aerosol. It goes through this way. Air flows through, so it was very handy for doing many, many, many tests. Excuse me for the siren out back. It could also test the pressure across that filter. So again, this has to do with how hard is it to breathe through, using a pressure sensor that would go to a computer. So it could do both. Yes, and here it is. This was, yes, built in my garage with the lathe I have in there. I considered having somebody redo it in stainless steel or something nice looking like aluminum or something that, but it wouldn't be any better, so it's never happened. So you can see there's an O-ring in here that is squished down when the top is squeezed down by this plate over the material. So it forms a very, very good seal. So there's no leakage around it. And you can then have air flow down through the top, and I can measure top and bottom, et cetera, to get an efficiency. Now notice 8 centimeters per second. That's a velocity. That's air velocity going through. That is equivalent to the 85 liters per minute through an entire N95. So that is the kind of equilibrating factor here, is to adjust the flow rate through this thing. So I also get 8 centimeters per second, because it's not the flow through it, it's the face velocity that causes changes in pressure drop and changes in efficiency. And that's the real guiding principle. How fast does it approach and go through the material, not this total flow rate, if that makes sense. If not, we'll move on. And then we have another adaptation of this, which is to use a mannequin to hold the mask, seal the mask around the mannequin head, and then measure the amount of particles just inside the mask and just outside the mask with these probes that are going into this plexiglass chamber into which the aerosol is going. So this allowed me to get truly up to 85 liters per minute and duplicate the NIOSH method to really closely in this sense. This has been used by other researchers at other institutions to do this. So back to this SMPS, it's not an aerosol photometer. It is this device. It's actually 2 devices and a computer that need to make it operate. And you can see this long column here and then this other box. I hate to say that these things are also extremely pricey and also built by TSI, 75,000 or more. So we had the money for this, but not the tester at the time. So how does this thing work? Well, it starts off with this long tube, and it's got a rod in the middle on which a voltage can be induced. And so there's a play between what's called the drag force on the aerosol going down through this column and the electrical force attracting it to the rod. So if I go to 1 voltage, particle isn't going to make it. It's just going to be caught up on this rod. But another size is going to be, and for a perfect type of voltage, it's going to spit out just 1 size only. So it can take multi-sized aerosol going in and spit out 1 size. Then the single size goes out to a counter. This counts the particles. So this device sizes, separates them, and the counter counts them. And then you can just start chunking through a distribution through. It starts off with the small ones, gives you their count, larger particles gives you their count, and marches you through a distribution over 1 minute to 3 minutes it takes to do the entire analysis. Now, what about the CPC over here? That's kind of a cool instrument too. These little particles are so small that you can't see them with a laser and diffract off that light like a photometer. So they first saturate them in a very humid environment, either alcohol or water, and then they cool that air to condense them. We're literally creating a cloud here. These are cloud droplet formations within this instrument. Now, as you can see, we've got particles that are large enough to be zapped by the light, the laser, and then, as you can see, it would march along, and knowing the size of these particles originally, now we can count them and come up with a distribution. So this really helps to get at the whole size effect thing as well as in terms of efficiency. So here are some results. So here's 2 upstream counts. You see squiggly lines. They're actually the little bin sizes. I should have probably put dots on every little measurement. And these are, so this concentration was very stable. We did an upstream count, downstream, and then upstream again. And so we took the average of the upstream, divided by the downstream, and come up with an efficiency. And so this is very similar to what I showed you kind of hypothetically or theoretically before, isn't it? And so then the efficiency curve that comes out of this is also, here's the dots, 1 for each one of these. So this area right over here, the lowest dip, one of those little points is the efficiency of the point close to this upstream versus downstream here in the middle someplace. So you can see, if you see, perhaps not, but you see way down the bottom left here, there's very little counts at all. So the difference between the upstream and the downstream isn't that much. We're getting to the limit now of statistical ability to actually come up with a good estimate of efficiency. So that's why it starts getting kind of noisy, especially at the low end. There just aren't enough counts to come up with a good estimate of efficiency, but we get the basic idea here. Okay, so with that, there were many tests to demonstrate that yes, the decontamination process was effective at decontaminating, sterilizing, and it did not affect the efficiency of the filters. So that was the major outcome of those studies that went back to the hospitals using the decontamination methods. So that was great for them. Some of them had to adjust their system, their vaporization process in order to make that happen. So we worked back and forth until they had the right kind of system to both get the viral kill they wanted and keep the mass from deteriorating too much. So then the other possible avenue here is to go at alternatives to the N95 material, maybe kind of create your own. So in order to do that, we have to make sure that these fabricated or designed materials or respirators would meet the N95 criteria in both efficiency and breathing resistance, and pass this fit test. Does it form a good seal against your face? So early on, I just checked out a bunch of different material types just to see what was going on. People were creating, masks. Everybody had their sewing machine going, right? I went into Joann's Fabrics back in April, I think, March or April, and I asked them, how many people are buying materials for a mask? And they said, everybody. That's the only reason we're selling cloth right now is to make masks. So, hey, rightfully so, though. So I tried different things. Ground cloth, that's a non-woven polypropylene material as well. So, maybe that would work. Didn't give the efficiency that was desired. There are certain types of grocery bags that are also the tough ones that are reusable, are also a type of non-woven material. Fairly good efficiency there. Shop vac bag, but you can see none of them were up near the 95%. Shemags, terrible, even though this particular said it can be used as a particulate filter, but obviously not the greatest. This is obviously breathing straight through it too. One other thought was sterilization ramp. This is material, as you can see down here in the bottom left, that they wrap. Let's see. Equipment, utensils, whatever, for surgical enterprises, surgical devices. So obviously it is autoclavable, it is sterilizable, so it already passes that test. And they noticed that the bacteria efficiency test that has to be done on a mask for any reason was way high. So they thought, hey, this will be a good substitute for an N95. But again, the bacteria test here is on much, much larger particles than the N95 test. So that was the downside of this. Now you're seeing the efficiency curve now, instead of being way up, notice the scale, there's 0.9 all the way down to 0, 1 to 0. This thing should be way at the top to be an N95 capable. And you see it dipping way down. It was still around 60%. That's because the aerosol used in the NIOSH method is over here. But unfortunately, we wrote up a paper on this with folks in Arkansas hospital and had to tell the world that no, sterilization ramp is not going to do the job. Again, getting back to these procedure masks or surgical masks, maybe they would work. What is their efficiency? They come in different levels with increasing efficiency. The procedure masks are the kind that they hand out all over the place. You see the ear loops. The ones used in hospitals or surgical masks have a strap on the back, so it's the easiest way to tell the difference between them. They all have different colors otherwise. These are the top ones. But again, maybe if you could get that thing to fit around your face really well instead of the gaps that are typically associated with it, maybe it could be an N95. So we tested those as if they're N95s. You can see that a level 3, which is the orange, still isn't up there around 0.95 where you would like it. But level 1s had a pretty wide variety of efficiency, neither of them either being where you want them. So a group here at Iowa came up with this idea. They call it the 8/8 rubber band hold downs. You can see, hopefully, that basically a way of manipulating these rubber bands so that they capture, and really press down around the face where you want it to get the fit you want. So this is a possibility. It wouldn't be an N95, but it would certainly get a surgical mask to be as tight fitting as possible, and therefore prevent any kind of leaks and give you the most protection possible out of them. So that also turned into a paper. They did prove that the fit factor, as it's called, they do fit well. They're above the 100 line, which is kind of the criteria there. And then there's commercially available filters out there. There's reasons for making filter material for other reasons than N95, so maybe they would work. And that got into the use of, or the thought that maybe we could print these 3D printed masks, could hold the filter material. If we can just find the right filter material, we might have an N95 in our hands. So this became a whole nother study with folks out at the Veterans Administration in Washington. You see the stopgap mask here that they used. And we went through more than a dozen different types of commercially available filter media. This one just happened to have 3 layers, but many of them only had 1. You can see it here on the mannequin head, and so we use the mannequin tester here. The one downside now is we're forcing all 85 liters per minute through that smaller area. That increases the velocity, which increases the breathing resistance and decreases the efficiency. So many of these materials that we came up with were possible if we could get them as big as a normal N95. That's what's going on here at 8 centimeters per second. So they, again, showed really good promise for some of them. But when we get them up to 42 centimeters per second, putting them into a 3D printer, the smaller filter area of the mannequin, you can see that the efficiency drops. So we're not quite there with this design idea. We have a paper out on this with a large group, including folks here at Iowa and out there in Seattle. And lastly is the thought of maybe just fabricating your own filter media, circumvent 3M or anybody else and design your own. And so there's a group here in our civil and environmental engineering program that has the capability of electrospinning fibers, as it's called, and they can create these fibers. And the cool thing about this is that if developed, then you could also add materials or compounds to the fibers to make them naturally kill off viruses. So after many attempts, as it says here, we are getting close here to a potential media that mimics the N95. So we're pretty excited about that, and we'll get a paper out on that pretty soon as well. So just wrapping up here, because I know I'm running out of time, just to give you some feel for, I've just been collecting websites and other places where people are getting pushing out some ideas on the next concept for N95s. So here's one. This is MIT. They call it the eye mask. And you can see here, the idea is to have a clear plastic so you can see the face better. You can see people's mouths moving a little better. Makes it a little more approachable. It's also can be sterilized. You can have disposable filters. And I hope now you can start assessing these things yourself by what I've been telling you. So what about the surface area here of those filters? Very small. So I'm not sure what they're doing here in terms of making these things breathable and still meet N95 capabilities. They don't say that, but that would be my concern over this design. So here's another group that probably did think about that, because wow, look at the size, and now see the surface areas as you increase it again, it's much easier to breathe through, because all that air is, it's just like breathing with your mouth wide open versus with your mouth just barely open, right? It's the same concept. So here they've got a reusable mask. They can sterilize it, and they can obviously replace the filter disc. So that's a possibility. Now we're starting to get really futuristic here. So this mask is, as you can see, has stuff and things inside it. And they call it the first antiviral face mask because it's got a UV light source within it. So it's a filter plus the UV light. And I believe, I should have looked into it, but I'm pretty sure this is a little pump in there as well to help pull the air through this thing to ease the breathing process. I don't know what this thing would weigh. It's another issue, but that's possibly where they're going, especially with the UV light. Here's another one, same kind of technology. It's a sensor within the mask detects the rate of the wearer's breathing and adjusts the speed of the fan accordingly to make breathing effortless. So that's pretty interesting. So it increases the fan speed. It's also got UV lights in it to kill germs. So that's pretty high tech. And here's another one. Apparently, again, clear face, trying to get it so people can see each other better. But this has got extremely small filter cartridges around the side. It's also got carbon filter to pull out organics. This would be great for someone with asthma, for example, and bioaerosols, pollens, and things that you don't want to have coming into your face, as well as the viruses. Here's this guy's got stubble beard, which we were all told is a no-no when you wear a mask because you're creating leaks around it, but we won't go there. This one apparently has an option for a UV light source as well. I wonder about, again, the small surface area of the filters here. And lastly, here's the Razer Hazel mask. This is to be used as a surgical N95, so it's completely sterilizable. It's also got active ventilation, and it's got voice amplifying speakers in it. So with that, I'll stop and take questions. Hope that's been educational to you and kind of what you expected out of this talk. But if there's other issues or thoughts you can have, I think we have a little bit of time to share those. And if you know what this graphic here is, you're at least 45, I would guess. So with that, I'll stop and answer questions. Thanks.
Thank you so much for your presentation. Yes, at this time, if you have any questions, you're welcome to enter them into the online Q&A box. For those who have asked, yes, this presentation is recorded and will be made available for reviewing on YouTube, and we'll send out a direct link to that tomorrow. Our first question, half-face FFR have protection factors of 10. Isn't the focus on filtration overestimating the protection provided?
Okay, so this is the dual issue of filter efficiency versus the actual wearing of the device and in terms of its potential to leak. So an N95, I guess you could say then, is not an optimal device. It doesn't work 100%. There are leakages around it, especially when you move your jaw, et cetera. So again, this gets back to that fit. If it fits well, you should have a 100, which means that only 1% gets through. You flip around the 100, it's 1 over 100, 100 over 1. But that's done at a normal breathing rate using particles that are just in the atmosphere, which are going to be larger than the 0.075. So I guess this question is getting at the realistic issue of wearing the thing and how effective is it once given the potential for leakage. Now that 10 is highly conservative, huge. Let's go the other way. The fit factor is 100, which is okay. For any particle greater than about 1 micron, it should be 1,000. It should be skyrocketingly high if there's a perfect fit. So I have issues with the 10 just to begin with. That's only taking out 10%. Only 10% get through. But yeah, it's a concern, and that's why in any of these designs you have to also consider ultimately how well this thing's going to seal against the face. I hope that answered the question. I don't know.
Thank you. Have manufacturers approved sterilization or disinfection of their N95 FFRS?
The manufacturers, no, they didn't get into the approval process. They gave recommendations, and I can possibly find if the questioner wants, can email me. 3M put out some really good advice on this issue. They never designed them, and they were first right up to say, we didn't design these things to be reused. So let's start there. And they left it up to the FDA to do the approval process. So I don't know if that, I focused in on the word manufacturer there, and the answer is no, they didn't do it. It was up to scientists and the manufacturers of the sterilization equipment primarily. And so I did get involved with one of those companies gratis. I didn't get paid by them, but yeah, so.
Thank you. Someone was also asking, what are your thoughts on the new ASTM standard for face coverings?
I don't know if I could go there. There are several floating around. I'd have to know specifically which one they're referring to. I know there are attempts, and I've been involved with some of these groups to determine some sort of more specific guidelines associated with face coverings themselves. So we've all been floating for the past year on this issue. Again, from anybody with a sewing machine on up. So, kudos to the ASTM for putting together a group to try to tackle that issue. And I'm not sure if it's been promulgated yet completely, but certainly within the next year, they'll have much better guidance on what constitutes a good face mask for the public.
Thank you. Another question, will you be testing the CDC's recommendation to double mask, for example, a cloth mask over a procedural mask, and to not untuck a procedures mask?
I've thought about that. I can only speak about that anecdotally in terms of my personal attempts at it. Any doubling of the mask, of course, is going to increase your breathing resistance. So we're almost starting to get to the point where we have to be careful of people with compromised lungs, right? And that's an issue with industrial use of N95s as well. You have to be cleared, medically to wear one if you're going to be forced to wear one as part of your job. So that concerns me there. However, it does, the addition of the second layer definitely pushes down everything. It helps form a seal much, much better than a single use. And so talking about fit factors or, leakage, of course, we all know, and we're actually reliant on that leakage when we put a mask on it. If you actually put that mask flat up against your face and try to breathe completely through it, it's difficult. And to do that nonstop for hours is extremely difficult. So back and forth we go on that, which is why they were used as source control, right? And I haven't been really talked about that here. It's the source. You are the source of the droplets spewing out of your face. And that's what that kind of bag in front of your face is there to capture. It's not anywhere near as effective at taking those little tiny aerosols that are floating around the atmosphere containing the virions and wafting over in your direction and preventing them from breathing it in. But I hope probably most of the audience would understand that at this point.
Thank you. This is kind of a follow-up in that direction. Can you please discuss the efficiency of surgical masks and cloth masks that are most available to the population? And do you feel that they should be used if the N95 is not available?
The cloth mask itself, and there's talked about Dr. Ranganasamy. He does have a 2010 paper out there. Again, in 2010, they were thinking this might be the only option we've got. So that is out there. You can Google Scholar Ranganasamy cloth face mask, and they're down around 40–50% efficient. They also are least efficient at larger particles. But again, we're all getting back to that issue of leakage versus not. So it all depends. Do you have a system where you can again apply it to your face and form a really good seal? And they were never designed for that in the first place. So then again, the adaptation to that was this rubber band concept I showed you, which was very, very effective. Another use of 3D printing was you can do a 3D facial scan and get the bumps and contours of a person's face, and then they molded a 3D printed kind of circular band around a person's face so they fit that over. So it's just doing the same thing as the rubber bands, but forming a perfect seal around your face to squeeze that surgical mask closer up. And in that case, you're getting real close to an N95. As a matter of fact, back to the fit test, I can guarantee you would pass a fit test with that kind of device. And I'll leave it go at that in terms of that comment. But it's surprising. Again, the fit test does not prove that it's an N95 that it passes the N95 criteria if you pass a fit test. And again, I don't know if I want to get too deep into that, but.
Someone was curious also if the last picture was Hill Street Blues.
Yeah. Yes, 2 points, right. I don't know why that flashed into my mind. I was finishing up the PowerPoint. I was like, yeah, hey, be safe out there, everyone, right? Who said that? Oh, it's Hill Street Blues guy, of course. Right.
Someone was also asking about UV light. Are there any hazards associated with UV light, especially so close to the face?
Yeah. I was just going to say, well, no, not normally, because, when they've used them to sterilize or decontaminate a bunch of masks, they would do it in a room, away from people. But yeah, they would have to have some sort of protection there for the wearer of a mask that's got this little UV light thing in it. I would assume that's part of the design, that they would block out that light from streaming directly onto skin. Yeah, that's a good thought actually, and would have to be part of the design criteria. Mhm.
Thank you. Another question, how do elastic straps do with the various sterilization techniques?
Yeah, as I skipped over that concept, and from my understanding, they do pretty well. But that was one of the big concerns. You lose, as we all know, you lose that strap and you've lost the whole mask. It's really hard to kind of staple it back on and get the thing working again or anything. And they do corrode. Ozone, for example, just eat them up. So the hydrogen peroxide, what they did was did determine that there's so many cycles that they could go through, and they said, okay, well, this kind of decontamination method is good for maybe up to 10 cycles, and after that, you better just chuck it. And I think beyond that, then hospitals went further down the road and said, okay, we're going to only reuse them 5 times, or maybe even only twice. We'll still save a lot. We'll still have a lot of reuse, but they pushed it down as far as they could to feel safe about it. And then the other issue is the metal nose band, right, is crucial to help forming a fit. And once you form it over one person's nose, it's actually kind of weird to try to rebend it to fit your face. So I don't know if they also went right straight back to the same user, or if they just said, okay, pick out of the pile of decontaminated masks, because that also is a concern in terms of getting a good fit the second time around.
Well, thank you so much for your time today, and thank you for the presentation. And also thank you to everyone who's joined us for today's webinar. The Education and Research Center Industrial Hygiene webinar series takes place the second Tuesday of every month. And this series is in addition to our ERC Ergonomics webinar series, which is the third Wednesday of each month. So again, this presentation has been recorded. You're welcome to check back and watch, catch up on it or share it. It'll be on YouTube. And I'll send a link directly out to that tomorrow in the follow-up evaluation from Zoom. And also our next industrial hygiene webinar will be on Tuesday, April 13th, and it'll be in partnership with New York, New Jersey Education and Research Center and Dr. Brian Pavlonis on estimating indoor transmission risks of SARS-CoV-2. You can learn more about these upcoming webinars at coeh.berkeley.edu/about-CE. And thank you again so much for joining us today. We really appreciate your time.
Yeah, okay, my pleasure. Thank you all. See you.